Right, today we're looking at anaerobic respiration and the energy systems, three different energy systems we've got in mammals. We're looking at 4A grades, we're looking at U and A and A star, suppose this is. We're looking at relating the demands of different sports to the three different energy systems that we have. For B grade, we're looking at explain how respiration can continue in the absence of oxygen, so anaerobic respiration, and then for C grade, just describing the ethanol pathway and the lactate pathway. For my specification, it's all of this here. Pause the video by all means, have a read through, you'll see where we're going with it. So, what we're looking at, I'm sure you're already aware that anaerobic respiration is how we make ATP when you've not got enough oxygen. You've seen already from the electron transport chain that the oxygen is used ultimately to soak up the hydrogen atoms that are produced at the end electron transport chain. So you've got the electrons, you've got the hydrogen ions. The electrons obviously bob onto oxygen, and that then attracts the hydrogen ions, and you're left with water. If oxygen's not available, then the electron transport chain Krebs cycle have to stop, otherwise you get this build up of hydrogen atoms, and obviously that'll be bad news. So they stop, glycolysis still continues, and glycolysis still produces hydrogen atoms, as you know, and so those hydrogen atoms need to be gotten rid of if respiration is to continue. There's two pathways that are available for anaerobic respiration. The first being the ethanol pathway. Now, this doesn't happen in mammals. This happens in microorganisms and yeast, as you can see, and it's how microorganisms are used to produce alcohol. So in terms of beer production, wine production, anything like that, then yeast is the organism that produces the ethanol that obviously gives the alcohol content to beers and wines. How it works, well, basically this process here is glycolysis. As you already know, glycolysis yields 2 ATP, and you also produce 2 NADH from that as well. So those hydrogen atoms are taken out from glycolysis, picked up by NADH, and the pyruvate is further metabolized into something called ethanol. So it's decarboxylated. Look, the carbon dioxide is taken off it. It's decarboxylated into ethanol, and then these hydrogen atoms are put back onto it, and that converts ethanol into ethanol, and that's how microorganisms produce ethanol. So it's a reduction, because you've got the addition of hydrogen atoms, that's a reduction, and the enzyme that controls it is this one here, alcohol dehydrogenase, or ethanol dehydrogenase, they'll sometimes call it. This can't happen indefinitely, because ultimately the ethanol poisons whichever organism it is that's producing it, and it's also irreversible, so they can't turn the ethanol back into ethanol and then pyruvate or anything like that. Once they've made the ethanol, that's it, it's made, and ultimately it poisons them and kills them off. For the chemists amongst you, this is, I mean, we've just looked at the reaction going in this direction, so from ethanol to ethanol. So you can see, look, the two hydrogens are added there and there, which are producing glycolysis, added then to the ethanol to turn it into ethanol, as you said, and that's where you get your content in your beer and your wine and so on. The second pathway, this is the one that we do get in mammals, is the lactate pathway. I'm sure you've already heard of lactic acid from GCSE study. So this is how it works. You've got glycolysis again occurring here, so your glucose being dehydrogenated and those hydrogens being picked up by NAD. You're getting your yield of 2 ATP out and so on. And ultimately what you're left with is pyruvate. Now, if there's oxygen is not available in an electron transport chain and Krebs cycle shut down, then pyruvate can't go into the link reaction and Krebs cycle. So what happens is these hydrogens here are added onto pyruvate, and that turns into lactate. So this does happen in microbes and in mammals, and it is reversible. So lactate can be turned back into pyruvate, or it can be metabolized. It can be turned into, and we fed into the Krebs cycle even, or it can be turned into glycogen if we needed to, and then that's stored in your muscles or your liver and used later on for respiration. So just looking here then, the pyruvate accepts the hydrogen atoms and it's changed to lactate by an enzyme called lactate dehydrogenase. Again, for the chemists, so those the two NAD, which have got obviously hydrogen atoms attached to them, that's meant to be a H, they're going to appear there, and that turns the pyruvate into lactate. The lactate ultimately going to build up in your muscles. It's going to cause cramps. It's going to stop your muscles from working. That's what exercise fatigue is when you're working at a high level. But like, as I said earlier, it is reversible and can be converted back, so you do recover. Although it might feel at times like you're never gonna. Okay, both the anaerobic pathways are bi in time, hence the title on the slide. Basically, they allow the organism to continue respiration and continue producing energy when oxygen's not available. I said this all already, so ethanol pathway is irreversible, whereas the lactate pathway is reversible, and as I said earlier, you can turn it back into pyruvate, turn it into glycogen and store it in the liver, or you can turn it into carbon dioxide and water, which you ultimately breathe out. Okay, this bit doesn't necessarily appear in the spec, but I thought I'd put it in anyway because it is relevant to some things we've done in terms of muscle fibres, and it's a possible question that can come up. Ultimately, the force that we've recorded been generated by one myosin filament acting on one actin is quite small, and overall, because you've got thousands of myosin molecules in any muscle, they say that overall the maximum force can be produced is about 40 to 50 newtons per centimetre squared of area of muscle. There's a relationship between the length of the muscle and the amount of force that it can produce, and ultimately, as I've written here, the more cross links you've got formed, the greater the force. So if you look at this part here, when the muscle's stretched, you've only really got these myosin heads acting, I should say that differently, these myosin heads connecting to the actin, so you've got less interaction, so you can produce less force. Here you've got more, if I colour it in, so you've got all of those myosin heads connecting with the actin, so you're going to generate more force, and here you can see all of those. So ultimately, when the muscle is at an optimum length, then it can produce a greater force. When it gets shorter, as you can see here, the force decreases because it's got less far to go. It can't interact any further because it's reached its maximum contraction. So there is a relationship ultimately between the length of the muscle and the amount of force it can generate, and about halfway through contraction is where you're going to generate the most force. So where does the energy come from for muscle contraction? That's the link. Well, you already know. ATP. I'm not going to tell you my biology joke. I'm sure it's etched in your brains there somewhere. But you know that ATP provides the energy that we need in order for lots of different activities in the body. But in this case, the interaction between actin and myosin. Now, your muscles only have a tiny amount of ATP in them, about enough for 3-4 seconds maybe of maximum activity, and after that it's gone. Obviously you can use your muscles for longer than 3-4 seconds, so you have systems, as you've seen, in terms of chemiosmosis and so on, to produce ATP for a longer period. But in the initial burst, that initial 10 seconds, you need another way of producing ATP, and what we use is a substance called creatine phosphate. And creatine phosphate is basically there to help your body make more ATP in a short space of time. How does it work? Well, basically, when you're resting, you use ATP, you take the phosphate off it, add it to something called creatine, and that produces what's called phosphocreatine on here, or creatine phosphate is what we're going to call it. Okay, so take the phosphate off your ATP, add it to creatine, you get creatine phosphate. Creatine phosphate can be stored. Okay, and then when you exercise, I'm not really sure cutting the lawn is exercise, but when you exercise, you then use that phosphate from the creatine. You can add it to ADP that is basically ATP that has been used, and that will form for you ATP that you can then use for muscle contraction again. So CP, creatine phosphate, is basically like a store of phosphates that you can then add quickly and easily to ADP so that you can continue muscle contraction. When you're doing that, you don't need to respire. So you got those first 3 or 4 seconds of ATP, and then for the next 10 seconds you can use the CP system. So if you imagine a 100-metre sprinter, they don't need to respire. They'll use the ATP in the muscles, then they'll use the CP system. So it's all anaerobic, and 100-metre sprint lasts between 10 and 12 seconds. So they don't need to respire effectively. They're just using this system in order to produce the ATP that they need. After that, if you go on any longer than that, then you'll start to need to respire on glucose, and that's where glycolysis will kick in. And that'll either kick in because you're working aerobically or anaerobically. In which case, anaerobically you're producing your lactate, aerobically you're using Krebs cycle, electron transport chain, and so on. Obviously, you know already, for it to respire aerobically, got to have a good supply of both oxygen and glucose. If you are exercising for long periods, your body ultimately will start to use its glycogen stores. So it's got glycogen stored in the muscles, it's got glycogen stored in the in the liver. And when glucose levels get low, it'll start to use that glycogen. It basically releases glucagon, which is a hormone that turns glycogen into glucose, and the glucose can be used as your substrate for glycolysis. They can also, if you are exercising for even longer periods, they can use fatty acids too. So if you're a marathon runner, for example, you'd be respiring fatty acids and not just your glycogen. But as we said, that burn that we've talked about and that anaerobic activity, when you are sprinting hard, if you're doing a 200 metre or a 400 metre sprint and so on, you get that burn in your legs. That's because of the production of lactic acid, which is basically produced because not enough oxygen is available. And that lactic acid stops your muscles working, causes things to slow down, ultimately stops you exercising, but the lactic acid goes away when oxygen's available again because you metabolize it into glycogen or carbon dioxide or whatever. If you have a quick look at this graph, it kind of summarises it. So the time along the bottom, you've got the time that you're exercising, and up the side you've got the energy that's being produced. So you can see the yellow is the ATP store, so that lasts, you can see here, 2 seconds. And once that's started to be used, your CP system kicks in. That's this one here. It's just creatine phosphate. You can see that line there. So that peaks and lasts as a maximum of about 10 seconds. After that, if you're still exercising, you then have to start to kick in the lactic acid system, which is basically glycolysis, isn't it? And then the pyruvate at the end being turned into lactic acid. So that's this system here, and that will quickly stop, because once you've built up too much lactic acid, you just have to stop. Your body can't deal with that anymore, and muscle contraction ceases. The blue one, the aerobic system, you can't work as intensely, so this has to work at a much lower level, but it can last for up to 2, 3, 4 hours, whatever. Depends on the intensity of what it is you're doing, but that'll keep going, just won't produce anywhere near the same amounts of energy as the other systems, or at least not in the same time frame. Finally, a quick look at this, something called oxygen deficit. So if you consider when you start exercising, so let's say we all go on, you go and run down the street or run up the stairs or whatever, your body's needs an instant hit of energy. It's got instant demand. So if you look here, this is where we start exercise. You start running up the stairs. You need this much oxygen in order to do that. Obviously, at the start, you're not breathing heavily, so you're not supplying your body with that amount of oxygen. So we say that there is an oxygen deficit. There's a difference between how much oxygen you need and how much you're bringing into your body. As you continue to exercise, then the amount of oxygen you bring into your body increases in line with the requirement, as long as you're not exercising really heavily and you're going anaerobic. So let's just say you're jogging down the street, you'll start to breathe more heavily. That oxygen will therefore be supplying your muscles with the oxygen that it needs, so that it can respire aerobically and continue exercising. You still have this purple shaded area here, though. You still have that. That's still your deficit. It's still there. Okay, and then you could exercise as long as you're doing it aerobically. You can exercise for a period of time, however long that is. Like we said earlier, an hour, 2 hours, whatever. At the end of the exercise, though, you need to pay off that deficit. And this used to be called oxygen debt. Regularly now it's called EPOC, or those who don't have an accent such as mine will call it POEC, okay, which is post oxygen exercise consumption. Alright, I prefer EPOC. EPOC's what I know. Exercise post oxygen consumption, whatever. We'll have a look on the mark schemes and see what they say, but it's the concept that matters, in that you stop exercising, you still breathe deeply, don't you? You run down the street, you stop, you don't just breathe normally instantly, you breathe deeply for a period of time to pay off that oxygen deficit, and that's what EPOC is. It's basically you paying back that oxygen that you used at the start when you weren't really ready for exercising. Those two should really be about an equal size. They're obviously not on this, but they should be. So oxygen deficit, and then EPOC used to be called oxygen debt, you paying back the oxygen requirement that you didn't have when you first started exercising. And that's the lot for this week. So looking at relating the demands of different sports, you'll have to think of some different sports that you know of and see which energy systems are being used in those sports. Explain how respiration continues when we've not got oxygen, and describing those two pathways.